Welcome back, everyone, to the deep dive. Today, we are diving into a question that is at the heart of research. Like, how do we actually know what causes something to happen, especially when the outcome is a straightforward yes or no?
Yeah.
Like, does this new workout plan actually lead to weight
Uh-huh.
loss, or did that new marketing campaign actually increase sales?
Yeah.
Fortunately for us, we have an excellent guide for this deep dive.
Okay.
The research article, Cause and Event, Supporting Causal Claims Through Logistic Models by Anne O'Connell and DeLeon L. Gray.
Okay.
This was published back in 2011 in Educational Psychology Review.
Gotcha.
Now, in this deep dive, we are going to try to unpack how researchers establish that cause and effect relationship, particularly when dealing with those yes or no outcomes.
Right. Those dichotomous outcomes.
Exactly, dichotomous outcomes.
Yeah.
And while this article focuses on a specific statistical method called logistic regression,
Right.
it also really stresses that making a strong case for causality involves much more than just number crunching.
Oh, absolutely.
It's not just about the math, right?
Yeah.
It's about the whole research design from the ground up.
Absolutely.
And this is important not just for academics, but for anybody, really.
Right.
Like, if you're trying to figure out if a decision you made had a certain outcome, or if you're evaluating information you come across, or if you're just curious about how things work, understanding these principles of causality is incredibly valuable, wouldn't you say?
It's fundamental to critical thinking.
Exactly.
Yeah.
And in this deep dive, we might even uncover some surprising limitations of statistical models, and we'll see just why a well-designed study is absolutely essential.
Yeah. Absolutely.
So, what should we even start with this?
Well, the article kicks off by really underlining this fundamental, drive in research, this real desire to figure out what works.
Mm-hmm.
O'Connell and Gray point out that across various fields, like psychology, education, public health, criminal justice, the list goes on, there is a strong emphasis on figuring out what truly makes a positive impact. They bring up some really important work by folks like Reel, Schneider, and Town,
Hmm?
who all emphasize this central goal of understanding how to make things better, improve outcomes.
Yeah.
That's a big part of what research is all about.
Right?
And it's a big part of what this article is really trying to get at.
Okay, so let's get right to the core here.
Sure.
One of the key takeaways from the start is that you can't just take your data, plug it into some statistical software program, and expect it to just spit out causal answers.
Yeah, if only it were that easy.
Right. If only.
The real strength of any statement about cause and effect hinges on how well the research itself is designed.
So garbage in, garbage out.
Precisely. Think of statistical methods as powerful tools,
Mm.
but they can only do their job well if the foundation, the research design, is solid, and if it minimizes potential biases.
Right.
And if it really thinks about all the other possible explanations for what we're seeing.
Right. You have to account for all those confounding variables, all those lurking variables.
Mhm. Absolutely.
So this brings us to the main statistical method that this deep dive
Yeah.
revolves around, and that is logistic regression.
Right.
So then the simplest terms, what is logistic regression and why is it like the go-to method when we're dealing with these yes or no outcomes?
Okay, so logistic regression, it's often shortened to LR.
Okay.
It's a statistical technique, and it's specially made for those situations where the thing we're trying to predict only has two possibilities.
Okay.
That's what we mean by a dichotomous outcome.
Dichotomous.
Like think back to the examples we started with. Did the student drop out of school or not?
Yes.
Did the marketing campaign lead to a sale, yes or no?
Uh-huh.
So it's different from your typical linear regression, which is what we use when we are trying to predict a number that can take on a whole range of values, like test scores or revenue,
Yeah. Yeah.
a continuous number.
Oh, okay. Yeah.
Yeah, and because a binary outcome, it's stuck between 0 or 1, like yes or no,
Yeah.
using standard linear regression just wouldn't make sense.
Right.
You need a different tool for the job.
So this is where logistic regression comes in.
Exactly, and it falls under a broader category called generalized linear models, or GLMs.
Okay.
And the authors point out three key parts of these GLMs.
Let's hear them.
Okay, so first up, you've got the random component.
Uh-huh.
And in logistic regression, this follows what's called a Bernoulli distribution,
Okay.
which is basically the probability of success or failure for a single event.
Got it.
Then you've got the linear component,
Uh-huh.
which is this link between a transformed version of what we expect to see in the outcome
Okay.
and our predictor variables, including any treatment or intervention that we're interested in.
Okay.
And lastly, you have the link function,
Okay.
which is this crucial bit that connects the actual outcome to that transformed version I mentioned.
Okay, so for logistic regression specifically, there's this thing called the logit link function.
Right.
What exactly does that do?
Okay, so the logit link, it's like this really clever mathematical trick. It basically stretches the probability scale, which normally goes from 0 to 1,
Yeah.
and it stretches it out to a scale that goes from negative infinity to positive infinity.
Oh, wow.
Right, so this lets us model the relationship with our predictors in a nice linear way,
Uh-huh.
even though probabilities themselves have that kind of S-shaped curve.
Okay.
It takes the probability of something happening and it transforms it into the natural logarithm of the odds of that thing happening.
Okay, now hold on. Let's break this down for our listeners.
Sure.
What exactly do we mean by odds in this context?
Right. Good question.
Yeah.
The odds are essentially the ratio of the probability of something happening to the probability of it not happening.
Okay, I'm with you so far.
Okay, great.
So the logistic regression model then figures out how this log odds of our success changes based on all these different factors we're considering, including whether or not someone received a specific treatment. Okay, so we've got logistic regression. It can model the probability of a yes-no outcome, but how do we actually draw causal conclusions from that?
Right. That's the million-dollar question.
Yeah, and that's where Rubin's causal model comes in, right?
Yes, Rubin's causal model, it's like a really useful framework for thinking about causality.
Okay.
And it basically says, you know what, determining if something causes something else, it's like trying to figure out what would have happened if things were different.
Okay, now you're getting a little bit too abstract for me.
Okay, let me put it another way.
Okay.
It's basically saying that we have this missing piece of information,
Uh-huh.
which is what's called the counterfactual.
The counterfactual, what's that?
It's basically asking what would have happened to someone if they didn't get the treatment, even though they actually did.
Okay.
Or, on the flip side, what if they did get the treatment even though they didn't?
Oh, okay.
Because, in reality, we can only see one outcome for each person.
Right.
So the other possibility, that other reality, that's the counterfactual.
It's like the road not taken.
Exactly, the road not taken.
Okay, so how do we deal with this missing piece of the puzzle then?
Well, a crucial assumption in Rubin's model is something called the stable unit treatment value assumption.
Okay, that's a mouthful.
It is. It is.
What is that? Like an acronym or something?
It is. It's often shortened to SUTVA.
SUTVA. Okay.
And what it boils down to is that one person's outcome shouldn't be affected by another person's involvement in the study
Okay.
or what treatment they get.
Okay.
So, like, your results shouldn't be influenced by what's happening with someone else in the study.
I see. So it's kind of like an independence assumption.
Exactly. You got it.
Gotcha. So when we're talking about trying to get as close as we can to understanding that counterfactual and establishing causality,
Right.
randomized controlled trials, or RCTs, are often considered the best way to go, right?
Yeah. The gold standard, they call
With
it.
the gold standard, yeah.
Yeah. And the article emphasizes that random assignment is so important because it helps to balance out any unobserved differences between our groups.
Uh-huh.
Between the group that gets the treatment and the group that doesn't.
Right.
And this helps to minimize selection bias.
Okay, now what do we mean by selection bias?
So selection bias is this sneaky thing that can happen when the groups in your study aren't really comparable to begin with.
Uh-huh.
Like, imagine if the people who volunteered for a new weight loss program were already more motivated to exercise and eat healthy than the people who didn't volunteer.
Okay, I see.
If you don't randomly assign people, you might end up with groups that are different in important ways even before the study starts.
Okay, so random assignment is like this equalizer.
Exactly.
It tries to make those groups as similar as possible, even on things we haven't thought to measure.
Right, so if you randomly put people into groups, on average, those groups should be pretty similar,
Okay.
even on things that we haven't even considered. Now, for these yes or no outcomes, the average treatment effect is basically the difference in the probability of success
Uh-huh.
between the treatment group and the control group.
Okay.
But when we use logistic regression, the article stresses that the odds ratio, which we shorten to OR,
Okay.
that's derived from the model, that is the best way to measure the causal effect.
Okay, we talked about odds earlier.
Right.
The odds ratio again. So how exactly does the odds ratio help us figure out this causal impact?
All right, so the odds ratio, it directly compares the odds of success, let's say in the treatment group,
Okay.
to the odds of success in another group, like the control group.
Okay.
So if the odds ratio is bigger than 1, it's kind of hinting that the treatment is increasing the odds of success.
Okay.
If it's less than 1, it's suggesting that it's decreasing them.
Uh,
And if the odds ratio is 1, it's like saying, well, there's no real effect here.
Got it. So if a study on a new job training program found an odds ratio of, let's say, 1.8 for employment, that means that the people who completed the program have 1.8 times the odds of being employed
Yeah.
compared to those who didn't, even after considering other factors, right?
Right. That's exactly it.
Okay.
Now, the article also looks at what happens when you just can't do a randomized controlled trial.
Right. Sometimes that's just not possible.
Yeah.
Or it might be unethical.
Right. Randomization isn't always feasible or ethical.
Right. Like sometimes you're looking at the effects of something that has already happened,
Mhm.
or it might be wrong to withhold a potentially beneficial treatment from the control group.
Absolutely.
So in these cases, what are our options?
Well, in those situations, researchers often use what are called quasi-experimental or non-experimental designs.
Okay.
And the authors really emphasize that even without that randomization, we can still make strong causal arguments, but we have to be very careful.
Okay.
We need to use methods that try to approximate that randomization process and account for that potential selection bias.
Right.
They actually mentioned some really important work here by Little and Rubin and Shadish and colleagues who are like the heavy hitters in this field.
So how do researchers try to mimic randomization when they can't actually do it?
Well, one design they specifically mentioned for these yes-no outcomes is the case control study.
Okay.
So in this design, you're basically comparing individuals who have experienced the outcome you're interested in, the cases,
Mm-hmm.
to a group that's similar, but they haven't experienced that outcome, the controls.
Right.
And then you kind of look back in time retrospectively and see what factors might have been different between those two groups.
Okay.
The trick here is to carefully match the control cases to the cases on important characteristics,
Mm-hmm.
so you can make those groups as comparable as possible.
So we're basically trying to make it as if they were randomly assigned.
Exactly.
Right. We're trying to get as close as possible to that ideal scenario.
Yeah, to isolate the effect of the thing we're really interested in studying. Now, another powerful set of tools they talk about are propensity scores.
Okay.
And what's really interesting here is that propensity scores themselves are often estimated using logistic regression.
Oh, wow. So the method we're talking about is also used to help us design those non-experimental studies.
Exactly.
That's pretty cool. How does that work?
Okay, so a propensity score, imagine it as the estimated probability that someone would end up in the treatment group
Okay.
based on everything we know about them before the treatment even happens.
Okay.
So we calculate these scores and then use them to create more balanced comparison groups, in studies where we couldn't do random assignment.
So we're not randomly assigning people, but we're using statistics to create groups that look like they could have been randomly assigned.
Yeah, that's a great way to put it.
Yeah.
Based on all the info we have, of course.
Right.
The article mentions a few ways to use these propensity scores.
Okay.
You can match individuals who have similar scores.
Yeah.
Or you can divide the sample into groups based on ranges of scores. That's called stratification
Okay.
or subclassification.
Okay.
Or you can use the scores to give different weights to people in your analysis.
Okay.
The main goal here is to reduce the bias that can sneak in when those treatment and control groups are systematically different, even before the study starts.
Right. So we're trying to control for those pre-existing differences.
Exactly.
And it's super important to include the right factors when we're calculating these propensity scores, right?
Oh, absolutely crucial.
Like even if some of them don't directly seem to predict the outcome we're interested in?
You have to include anything that might influence who gets selected into that treatment group,
Okay.
even if those factors aren't strong predictors of the outcome itself.
Right.
And this helps make sure you're balancing out all those things that led to the differences between the groups in the first place.
But even with these methods, we can't account for absolute or everything, right?
Yeah, that's a reality of research.
Like what about hidden biases, things we couldn't measure or didn't even think to measure?
That's a great point. And the article highlights this need for something called sensitivity analyses.
Okay, what are sensitivity analyses?
So these are techniques where you basically explore how much your conclusions might change
Okay,
if there were unmeasured variables that are linked to both the treatment and the outcome.
I see.
It helps you understand how much those hidden biases might be affecting things.
So even if we've done our best to approximate randomization,
Right.
a good researcher is still going to acknowledge those limitations and try to see how sensitive the findings are to those potential unmeasured factors.
Exactly. It's about being transparent and honest
Hmm.
about the limitations of your study.
Right.
Now, even if you have a really strong research design, whether it's a randomized controlled trial or a well-done non-experimental study, the authors point out that there are other really important design elements that you can't ignore.
Okay, so what else do we need to watch out for?
Well, first things first, your statistical model needs to be correctly specified.
Okay.
And this means making sure you've got all the right variables in there
Uh-huh.
and any important interactions between those variables.
Okay.
The article gives a good example here where they talk about how a student's GPA might affect their likelihood of dropping out of school.
Okay.
But that relationship might depend on how much they feel like they belong at that school.
I see.
So if you ignore those kinds of interactions in your model, you might end up with a misleading picture of what's going on.
It's not always a simple A causes B situation.
No, sometimes it's more like A causes B, but only under these specific circumstances, C. So
Exactly.
you got to watch out for those interactions.
Right. What else?
Okay, other things to consider. You need a sample that really represents the population you're interested in.
Uh-huh.
You need to make sure the treatment was implemented properly.
Right.
That's
Yeah.
called treatment fidelity.
Treatment fidelity. Okay.
Yeah, you need good measurements for all your variables.
Yeah.
Accurate and consistent, valid and reliable, as we say.
Got it.
And you need to handle any missing data carefully, like people dropping out of the study.
Right. Attrition. Yeah.
Yeah, attrition, exactly.
So lots to think about.
It is. And finally, you need to check that your model actually fits the data well
Right.
and that there aren't any unusual outliers that are skewing your results.
Got it.
So it's really this whole package deal.
A good design, good data, a well-specified model, and you got to be on the lookout for potential problems.
Yeah, all of that working together.
Okay, to kind of hammer these points home, the article includes a table with some specific recommendations for interpreting logistic regression results when the goal is to support those causal claims.
Right, it's like a cheat sheet.
Yeah, so let's go through those.
Okay, the first one is all about the research design itself.
Okay.
They really stress that you need to describe your study design clearly and thoroughly, so readers can understand its strengths and weaknesses in the context of your research question.
Right, you can't evaluate a claim if you don't know how they got the evidence.
Precisely.
Okay, what's next?
The second recommendation focuses on the link function in logistic regression.
Uh-huh.
Now, we talked about the logit link. It's the most common one for binary data,
Right.
but it's not the only option.
Okay.
The authors suggest researchers should justify why they chose the logit link
Okay.
and maybe even consider other link functions, especially when dealing with events that are super rare or super common,
Okay.
like the probit link or the complementary log link.
So different link functions might be better depending on the data.
Exactly. The logit link has advantages in terms of how we interpret the results,
Right.
with odds ratios,
Uh-huh.
but for really high or low probabilities, other links might just fit the data better.
Gotcha.
Okay, the third recommendation is about including all the important predictors in your model.
Okay.
You can't just toss in everything you measured and hope for the best. You need a good reason, a theoretical reason, for each variable and each interaction you include.
Okay.
And you got to link those back to previous research
Yeah.
and a clear understanding of what you're studying.
Okay. And the fourth recommendation, that's about propensity scores.
Yes, or other methods you use when you can't randomize.
Mm.
The authors really stress that you need to explain and justify how you use these techniques,
Okay.
whether you did matching or subclassification or weighting.
Right.
And you got to show those sensitivity analyses that check for hidden bias.
Okay, so we've covered design, we've covered model specification. What about the data itself?
Right, so recommendation number 5 is all about sample size.
Sample size. Okay.
And this is a tricky one with logistic regression.
Okay.
It's not just about the total number of people in your study.
Uh-huh.
It's also about how those outcomes are distributed.
Okay.
How many successes, how many failures you have,
Right.
and how many events you have compared to the number of variables in your model. The authors point out that small sample sizes can actually make your odds ratios look bigger than they really are,
Okay.
which can make effects seem stronger than they actually are.
So just having a lot of participants isn't enough.
Right.
You need enough data within each outcome category to get reliable estimates.
Yeah, they mentioned some general rules of thumb,
Right.
like having at least 10 events for each variable you put in your model.
Okay.
But they also say, these are just guidelines. You need to adjust them based on your specific situation.
Right. And you mentioned sparse data before,
Right, sparse data can be a problem.
where you don't have enough observations for certain combinations of variables.
Yeah, exactly. It can make your model unstable.
Okay.
And they also mentioned something called separation.
Separation.
Yeah, where your predictor perfectly or almost perfectly predicts the outcome.
Okay.
That can also mess things up.
Interesting.
Imagine if everyone who got the treatment had a positive outcome
Okay.
and no one in the control group did.
And
That perfect prediction can actually cause statistical issues.
okay, so that's something to watch out for.
Definitely.
What's the next recommendation?
Number 6 is all about interpreting those effects through odds ratios correctly.
Okay.
The authors really hammer this point home.
Mm-hmm.
They say you should use the odds ratio for the treatment variable as your main estimate of the causal effect
Okay.
for those binary outcomes.
All right.
And here's the crucial part. They explain the difference between odds ratios and relative risk.
Yes. This is where a lot of people get confused.
It is. It is.
So can you clear that up for us?
Absolutely. So the odds ratio, it compares the odds of something happening in one group to the odds of it happening in another group.
Okay.
But relative risk compares the probabilities
Mm-hmm.
or the risks of that event happening.
Okay.
They actually give a good example here, a hypothetical one, about a school dropout prevention program.
Okay. Let's hear it.
So let's say the probability of dropping out was, say, 0.17 in the program group
Okay.
and 0.21 in the control group.
Okay. So lower for the program group.
Right. Now, the odds ratio in this case would be about 0.77,
Okay.
while the relative risk would be around 0.81.
Okay. So both suggest the program is helpful,
Right.
but the numbers are different.
Exactly. And the key here is that the odds ratio often overestimates the relative risk,
Uh-huh.
especially when the event is more common.
Okay.
And the authors stress that you should interpret the odds ratio as a ratio of odds,
Okay.
not as a direct ratio of risks.
Right.
So in this dropout example, we would say that the odds of dropping out for a student in the program
Uh-huh.
are 0.77 times the odds for a similar student not in the program.
Okay.
They even mention a correction method by Zhang and Yu
Huh?
from way back in 1998.
Okay.
If you really want to interpret odds ratios as approximate relative risks.
Okay, so it sounds like misinterpreting an odds ratio as a relative risk can lead to some pretty big misunderstandings about the actual impact of something.
It absolutely can, and the authors argue that it can even undermine the credibility of your findings.
Wow.
Recommendation number 7 is all about model fit.
Okay.
So to really check if your logistic regression model is doing a good job, you got to look at a few things.
Okay.
First, does the model get better when you add your predictor variables?
Okay.
That's where tests like the chi-square likelihood ratio test come in.
Right.
And second, how well does the model as a whole actually describe what you saw in your data?
Uh-huh.
That's where goodness of fit tests like the Hosmer-Lemeshow test come in.
So we want to see if adding those predictors actually matters and if the model's predictions line up with what we actually observe.
Exactly. But the authors caution that these statistical tests, they're not the be-all and end-all.
Okay.
Just because your model fits the data statistically doesn't mean you've got the best model,
Right.
or that it truly reflects those causal relationships.
Okay.
So they recommend using other ways to judge your model's quality,
Okay.
like predictive efficiency,
Uh-huh.
which is how well your model correctly classifies the outcomes,
Right.
and something called pseudo-R-squared statistics.
Pseudo R squared.
Yeah, but they point out that there isn't really one agreed-upon measure for that in logistic regression.
Okay, so we're looking for a model that not only fits the data statistically,
Right.
but also makes sense in the real world
Yes.
and has good predictive power.
Absolutely.
Okay, and what's the last recommendation?
The last one is about multi-level models.
Multi-level models, okay.
So if you're looking at treatment effects across different groups or settings, like different schools or communities,
Okay.
multi-level analyses can help you see if that treatment effect varies across those contexts.
Right.
But they also advise caution against drawing strong causal conclusions just from that context-level variability.
Oh,
Because
okay.
multi-level logistic models can be tricky to estimate.
I see.
But they do say that these multi-level designs can be really useful for replicating findings across different settings,
Right.
which can make your causal claims even stronger.
So if you find the same effect in different places, that gives you more confidence.
Yeah.
Okay, so taking a step back from all this, it seems like figuring out cause and effect, especially with those yes-no outcomes using logistic regression, is pretty complicated.
It is. It's not a simple task.
It's not just about running the numbers, it's about the whole research process.
You got it. The design, the data, the analysis, all of it matters.
And a well-thought-out research design is absolutely crucial.
Absolutely fundamental.
Logistic regression can be a really powerful tool,
Mm-hmm.
but it's only as good as the study it's used in.
Right. You can't just throw stats at a bad study and expect miracles,
Right.
you know?
So we need to interpret those odds ratios correctly.
Yeah.
Think about sample size, model fit, and always be aware of those limitations.
Especially when you couldn't randomly assign people to groups.
Exactly, and I like that quote that you mentioned from the article.
Oh, yeah.
All models are wrong, but some are useful.
It's a classics.
It is a classic, so it reminds us that these models are just tools. They're simplifications of reality.
Right. They're not perfect representations of the world.
Right, they're representations.
Yeah.
So for our listeners out there, when you hear claims about what causes what,
Hmm.
especially when those claims are based on statistical models, how critically do you consider the research methods and their limitations?
Yeah. Do you just accept the findings at face value, or do you dig a little deeper?
Because figuring out what causes what is a process.
It is. It's a journey.
And we're all on that journey together, researchers, policymakers, and everyone trying to make sense of this complex world.
Absolutely.
So we encourage you to keep exploring these topics.
Yeah. Research design, statistical inference, it's all fascinating stuff.
It is.
And it can help you make better decisions in your own life.
Thank you so much for joining us for this deep dive into the world of causality and logistic regression.
My pleasure.
Until next time, keep those critical thinking skills sharp.
And don't be afraid to question everything.
And we'll see you on the next deep dive.
See ya.